Okay, this is part 2 of Unit 8C, and now we're looking at carrying capacities and real growth models. Now, if you think back to Unit 8A, we looked and found that exponential growth cannot continually carry on indefinitely. With the bacteria, we found out that the Earth would be covered in bacteria in a very short amount of time, which is just not possible, and we don't see that. So humans cannot continue to grow much longer at its current rate because we'd be, elbow to elbow over the entire Earth in just a few centuries. And so, theoretical models of population growth therefore assume that population is ultimately limited by the carrying capacity of the Earth. Or in other words, the carrying capacity is the number of people that the Earth can support. Because at some point in time, again, you can only fit so many people on the planet, and we can't keep doubling. And so, the carrying capacity in general is the maximum sustainable population. That's the largest population the environment can support for extended periods of time. And so the logistical growth is something we're going to be looking at that models this. And it assumes that the population growth rate gradually decreases as the population approaches the carrying capacity. And so, if the carrying capacity is 12 billion people, for example, a logistical growth model assumes that the population growth decreases as that number is approached. And the growth rate falls to zero as the carrying capacity is approached, allowing the population to remain steady at that level thereafter. And here's kind of a picture of that scenario. So you've got your exponential growth here, which for the population it's not sustainable. We can't continue to grow like that because we eventually come across this restriction, this carrying capacity line. So what happens is we see this tendency, this curve where it grows up, and then we start to level off at that carrying capacity. And sometimes when we're trying to find that carrying capacity, what will happen is you might see little spikes. So your population may jump over, but then you realize that we can't sustain that many people or that big of a population. And so sometimes you'll see little spikes like that as we try and approach this. But this is, in general, the nice clean model of logistical growth. So this is what we're talking about, exponential versus logistic. So here's this logistic growth. We are not going to be covering this super in depth, but just give you an idea. So when the population is small relative to the carrying capacity, logistic growth is exponential. When that population is small. So when the population is small compared to the carrying capacity, then that fraction becomes negligible, and so we just grow at our base rate here, or our growth rate. So our base growth rate of R, that's what we were looking at earlier. However, as population approaches the carrying capacity, the logistic growth rate approaches zero. That means we're kind of flatlining on our growth. We're not growing, we're not increasing, we're not decreasing, we're flattening out. So the fractional logistic growth rate at any particular time depends on the population at that time, the carrying capacity, and the base growth rate R, which we have looked at already as that base growth rate. So here's the relationship down here. The logistic growth rate is that base growth rate R times 1 minus the population divided by the carrying capacity. So now we're going to look at an example of that again. We're not going to dive heavily into this, but just so you have an idea as to the difference of exponential versus logistic growth and carrying capacity and how that can taper off that exponential growth. So if we look at this question, the world carrying capacity, so for the given carrying capacity, use the 1960 annual growth rate of 2.1%. and population of 3 billion to predict the base growth rate and the current growth rate with a logistic model. And then we're going to assume again our current population is 7.5. And how does this growth rate compare to the actual growth rate of about 1.1% per year? So that's a lot of stuff. So let's take this one at a time. So the first thing that we want to do is, we want to look at and find that base growth rate. So we want to know, what is this base growth rate here? Now in our formula, the base growth rate was R. So we actually need to find R in this case. So just using some simple algebra, we're going to divide both sides by this 1 minus population over carrying capacity on both sides. Carrying capacity to find our base growth rate that we have. So when we take a look at the numbers we have here, so again, R is the logistic growth rate, and for our logistic growth rate here, we're going to be using the 1960 number of 2.1%. So that would be 0.021, and then we divide it by 1 minus our population. Oops. So 1 minus our population of 7.5 billion. So I'm just going to do 7.5 billion, and our carrying capacity tells us in this example is 9 billion. So our logistic growth rate here, or excuse me, our base growth rate here is going to be, if I do this out in a calculator, I'm going to get approximately 0.0315 or 3.15%. Again, that's looking off of information from 1960. And so now, when we have that information that we can grab from 1960, okay, we're going to try and find the current growth rate with a logistic model. So again, this is based off of 1960 data. But what we can do now is we can say the 2017 growth rate, when we look at it here, is going to equal 0.0315, that base rate that we found, times 1 minus the population over the carrying capacity, which is 0.0053 when I type that in the calculator, or 0.53%. And so then when we compare our growth rates, we got 0.53% in 2017, and the predicted growth rate, so this is our predicted growth rate based off of some previous data that we have from 1960. And how does it compare to the actual growth rate right now? Well, in 2017, which is 1.1%, in this case, the growth rate of 1.1% is greater than 0.53%, and so we would say, I think I just said that backwards, I apologize. So the predicted growth rate of 1.1% is greater than, that says greater than, the actual, which was 0.53% when we look at the actual data. And so it looks like what's happening here is we're, based on, when predictions were made, we predicted it would be growing at about 1.1% per year, but it looks like that logistical growth is taking over, and our prediction versus our actual, the actual is less, and so we're starting potentially, and that's, again, this is based off of a 9 billion carrying capacity, but it looks like we're starting to see this part of the curve where it starts to level a little bit. But again, we don't know the actual carrying capacity. We have estimations, but we don't have the precise number. We won't know it until we actually get there. But scientists are doing their best to make different predictions. But again, this is just the basic idea. You won't be diving too deep into this in this class, but this is just a brief look at logistical growth and how we compensate for exponential growth that keeps going on and on forever, when in reality that cannot, it is not feasible, I should say. So if you have any questions, let me know, but that is Unit 8C.